Okay, so let's talk about molecular covalent bonds. And really all this means is uh, atoms or elements that have come together to make molecules, and how have they bound together? By sharing their electrons, right? So depending on what the elements are, their outer shell of electrons might want an extra electron, or it might want to share an electron to complete another element's outer shell. Okay, so covalent just means sharing of electrons. And many molecules in the body use covalent bonds to bind together. Carbon, hydrogen, oxygen, nitrogen, many others form covalent bonds. Okay, remember, carbon, you're going to see, is really the backbone element of most organic compounds in the body. So you're going to see carbon mentioned a lot. For example, even just sugar. So glucose, what's the backbone of glucose? Carbon. What's the backbone of triglycerides? Carbon. So carbon is really everywhere in the body. Okay, and here we are looking at different covalent bonds of molecules. And as I mentioned, it's really just the sharing of electron pairs. So hydrogen, it's sharing an electron each, making 2 electrons in the shell. Oxygen, O2, so two atoms of oxygen combining, making a molecule. CO2, so 1 atom of carbon, 2 atoms of oxygen that are sharing electrons and forming covalent bonds. Okay. Nitric oxide, there's an example of covalent bonds because they're sharing electrons. Same idea here. I won't go into any significant detail on this slide. Again, it's just the sharing of electrons that form a covalent bond. With hydrogen, it's the sharing of 1 electron from each one. With oxygen, there's actually sharing of 2 electrons. And that's why you get a double bond, right? A double covalent bond. And we signify that with 2 lines between the O for oxygen on the right side. So hydrogen, a single bond. Oxygen is sharing 2 electrons, so we put double lines. Okay, what's the term polar covalent bond? Well, it's still a covalent bond, meaning sharing of electrons, but one atom has a much greater pull and influence on that electron. So if you look at H2O here, water, sure, oxygen wants to take the electron from hydrogen, and hydrogen is happy to share the electron, but oxygen is a much bigger atom. It has more atomic mass than hydrogen, so there's a greater pull of the electrons towards the oxygen nucleus. So that makes H2O slightly what we call polar, meaning the electron from hydrogen has been pulled a bit closer to the oxygen part of the molecule, making it a bit negative, and the hydrogen molecule is positively charged because oxygen just wanted the electrons, didn't want the proton. So the proton is being repelled out a bit because it doesn't want to get too close to the protons of the oxygen. So we could call this a polar covalent bond. Okay, so even though they're sharing electrons in a covalent bond way, if one molecule has much more influence, there can still be a slightly negative charge on one side of the molecule and a slightly positive charge on the other side of the molecule, and that's going to determine how it interacts with other molecules in the body. Okay? Okay, and here's a water molecule, which is a perfect example of a polar covalent bond. They're definitely sharing the electrons, but just because of the size of oxygen compared to hydrogen, it pulls the electrons closer to the oxygen, making it slightly negative on that side, and slightly positive on the hydrogen side. So you can imagine when water's floating around in the body, because we're basically composed of large amounts of water, it has a slightly negative charge and a slightly positive charge to the molecule. Okay, and this is just showing you why it matters, because it's going to determine how water lines up with other water molecules, right? So the slightly charged hydrogen side of it is going to be attracted to the slightly charged negative side of the water molecule oxygen, right? So because of that, water has some strength to it when it's separating. And you can imagine that when you're filling a glass with water, and if you fill it right to the top, you can almost get over the top of the glass with the water, because water molecules are holding on to each other. So they're polar covalent bonds. Okay? So and that's why water tends to, for example, hang out in droplets. And when it comes to another droplet, they immediately come together and make a bigger droplet, because there's polarity. There's some attraction between the hydrogen part of the water molecule and another water molecule's oxygen. Okay, so let's look at a covalent bond versus an ionic bond. So covalent bonds involve the sharing of electrons between atoms, right? They want to complement and fill their outer shells. In the image on the left, that's a covalent bond. They're sharing the electron, which is depicted in red. An ionic bond is the attraction of two atoms because of being oppositely charged, right? So the ion sodium, which is Na+, is attracted to the chloride ion, which is negatively charged, right? That's ionic. Okay, so ionic bonds involve the electrostatic attraction between oppositely charged ions, and often it can result in the loss or gain of an electron. Now, ionic bonding often results in what are called an anion and a cation, right? Because there's usually the gain of an electron or the loss of an electron from an atom. And then one of them is left with a positive charge and one of them is left with a negative charge. And that's what we refer to as anions and cations. And we'll talk about those next. Okay, so we've already spoken about what ions are, right? They're atoms or molecules that have gained or lost an electron. So they become positive if they've lost electrons, one electron, two electrons, or they become negative if they've gained electrons. Now, we call an ion a cation if it's positively charged, such as sodium is a cation. We call an ion an anion, anion, if it's negatively charged, okay, such as chloride, Cl minus. So Na plus, sodium ion, Cl minus, the chloride ion, okay? And ions will create currents within the body because there's electrostatic pull between oppositely charged ions. Okay, so you're going to see that this will matter when we talk about electrolytes in the body, such as Na plus, Cl minus, K plus, which is potassium, Ca2 plus, which is calcium. Okay, so there's ions and cations that are interacting in the bloodstream and in the body. Okay, so let's look at some definitions here. And we're going to talk about a solution. Well, a solution is a mixture of a solute and a solvent. So let's use, again, salt and water. So the salt is going to be the solute. It's the part that you're putting into and hoping that it is dissolved into the solvent, right? The solvent is the substance that does the dissolving of another substance, which is the solute, okay? And typically a solvent is a liquid, such as water. So when we're putting a solute, such as salt, into a solvent, such as water, we may want to know what's the solubility of this substance. So salt, which is NaCl, easily dissolves into the solvent called water. If we add, say, oil to the solvent water, there's going to be next to no solubility. They don't want to get together at all. The oil is just going to float on top. It's not going to form a solution at all. Okay? A solution means that the solute has dissolved into the solvent. What's the concentration? Well, if you put a bit of salt in water and then you taste it, you'll have a weak taste of salt in the solution. If you happen to pour the whole box of salt in and then you taste it, you're going to have a very powerful taste of salt because the concentration is very high. So concentration is really telling us how much of the solute is dissolved within the solution. So what's the most abundant solvent in the body? Well, it's water, right? Water is basically everywhere in the body. We're composed of approximately 65% water. So if we were just broken down into our elements and molecules, 65% of our entire body would just be water, okay? And why does water matter so much in the body? Well, it allows us to make all kinds of solutions. right? So what about the saliva in your mouth? That's mainly going to be composed of water. What about keeping the mucosal linings of your digestive tract moist? That's going to be from water. What about flushing out waste through your kidneys in the form of urine? The majority of urine is going to be water. Lubricating joints with a special fluid called synovial fluid. That's mainly going to be composed of water with some proteins within it. Okay, what keeps the blood flowing? What's the main component of blood? Well, it's plasma or serum, but it's mainly water, right? So it's not like we have oil running through our system like a car. We basically have water-soluble blood flowing through our arteries and veins, okay, to help us deliver nutrients such as oxygen and glucose to all parts of the body to feed the body, okay? So what else does water do? Well, water can also control the temperature of the body through producing sweat and breathing out water molecules with respirations, right? So if your body wants to keep your temperature in very tight parameters, which it does, if you start to get hot, it can release heat in the form of sweat, or it can release heat in the form of you breathing out water molecules in your breath. Okay, so water is extremely important in the body. Okay, so in this example, just briefly, there's a broth. So the broth part is the solvent. What's the solute? Well, it's the salt that was added. So the mixture is now called a solution. So a salty broth is the solution. The solvent being the water, the solute was the salt in this case.